Hello everyone and welcome to Physics 220 here at Grantham University. This is our last week, Lesson 8, which covers the laws of thermodynamics. So what I'm going to do here is go through each of the laws and then we'll talk about the implications of each, talk about some different fundamental thermodynamic properties, and then I'll end the lecture by going over an example. So this might seem odd, but there were originally three laws called the first, second, and third law, but then physicists realized there was a more fundamental law, so instead of renumbering, they just made a zeroth law. So basically there's four fundamental laws of thermodynamics, numbered 0, 1, 2, and 3. So here's the first or zeroth law. It says if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A and C are also in thermal equilibrium also. Kind of makes sense and is common sense, but they had to really state this and get the point out there. And an important thing to realize is what thermal equilibrium means here. It means two things. One, the temperatures of the two objects are the same, and then thus, as we've seen through all the other examples in Lesson 7, there is no transfer of energy or there's no heat exchange. So that's what's very important there. Now, the first law is that the change in the internal energy of a system is equal to the heat added minus the work done by the gas, or delta U equals Q minus W. Now this is the actual most useful one. It's the most powerful law of thermodynamics. And it's very important to realize the signs, okay? So the heat added, so Q, which is positive, minus the work done by the gas, okay? So when the gas does work, it's subtracted off from there. When you do work on the gas, it's the other way around. Okay, this will tend to be the one we'll focus on the majority of this week. Second one is the total entropy of any system plus that of the environment increases as a result of any natural process, or delta S is greater than 0. What this means is the universe tends towards disorder. The systems and processes go from an ordered system to a disordered system. It's actually kind of a complicated subject when we get into, or when one gets into higher levels and we deal with the kinetic theory of matter or the atomic theory of matter. It tends to make a little more sense, but we'll kind of just leave it there as we go there. And the last one is kind of like a hard rule restriction. It says no object can be cooled to a temperature of absolute 0. The reason for this is, as we talked about last week, temperature is actually a measure of an internal energy, and what you're saying, if you can cool an object to absolute 0, you'll be removing all of its internal energy. Again, like I said, all three laws are important, but to be honest, we tend to focus on the first law. And that's what we'll see through the next 3 slides here. So now let's focus on the first law of thermodynamics. So I start by restating this from the previous slide. The change of an internal energy of a system is equal to the heat added minus the work done by the gas, or delta U equals Q minus W. The key point here are the signs of the Q and the W. Q is the heat added, so this means that there's heat taken out of the gas. Q is negative. For the work is the work done by the gas. So if there's work done on the gas, the W is also negative. And we could see from our lectures last week that the heat taken out of a gas follows the calorimetry equation, where Q equals Cm delta T. And the work, on the other hand, comes from the equation work equals P delta V, where a change in volume under a constant pressure does work. The other thing of interest here is what delta U equals, and remember the internal energy of a system is proportional to the temperature. So this comes into play when we look at the processes on the next slide on how a constant temperature or an isothermal process plays into our different discussions. Okay, our next thing here is what is called thermodynamic processes. We look at each of these and also talk about the implication of the first law, and then I'll review all the implications at the very end also. Our first process is called isothermal, which means there's no change in temperature. The key is because no change in temperature means no change in internal energy, or delta U equals 0, and then we see the first law that becomes Q equals W, where the heat added is equal to the work done by the gas. Next is the adiabatic, when the heat is 0. Or Q equals 0 means no heat flow in or out, and this can actually happen in a physical system. And in this case, the first law is then delta U equals negative W, or the change in internal energy is equal to the negative of the work done by the gas. There's also isobaric, delta P equals 0, and isovolumetric, delta V equals 0. The latter being more important because when delta V equals 0, double equals 0, or the work done equals 0. So then the first law here is delta U equals Q, or the change in internal energy is just equal to the heat added to the gas. Again, the key point here is that you have specific processes like this, then you can modify the first law accordingly. Again, kind of recapping, isothermal delta U equals 0. So this gives Q equals W. And in adiabatic, Q equals 0, or this gives the change in internal energy is equal to negative W. Or last but not least, in isovolumetric with W equals 0 gives delta U equals Q.
So let's take a second here to look at a few examples. Thermodynamic processes are very important to real-world examples, especially if you ever work with heat exchange, mechanical systems, so on and so forth. So I'm going to do two here. We'll start with this one. This is a gas is enclosed in a cylinder fitted with a light frictionless piston and maintained at atmospheric pressure. When 1400 kilocalories of heat is added to the gas, the volume is observed to increase slowly from 12 cubic meters to 18.2 cubic meters. Calculate A, the work done by the gas, and B, the change in internal energy of the gas. One thing I always like to point out here when doing these problems is notice it says 1400 kilocalories. A kilocalorie and a food calorie are actually the same thing, meaning when you read the amount of calories that something contains on a candy bar or a soda or whatever, that's actually a food calorie, and that's actually 1,000 times larger than a calorie we use in here. The way they distinguish those is a food calorie has a capital IC, whereas a regular calorie does not. Okay, so a couple things we want to point out. First, notice it's maintained at atmospheric pressure, which means it's a isobaric expansion. The work done by the gas at a constant pressure is from equation 15.3, and it is work equals P times delta V, where pressure is what we're using in question, and delta V is the change in the volume. So pressure is 1 atmosphere, but 1 atmosphere isn't always helpful, so we're going to convert it to pascals here. And the reason why we do that is, remember, a pascal is a Newton per meter squared. So it's 1.01 times 10 to the 5. It's almost exactly 1 times 10 to the 5, but not quite. So that gives us 1.01 times 10 to the 5 newtons per meter squared times the change in volume, which is 18.2 minus 12.0 meters cubed. So it's going to be 6.2. And notice what happens when you multiply meters cubed by newtons per meter squared. You get a newton per meter, which is going to give us a total amount of work done by the gas of 6.262 times 10 to the 5 joules. Now, and this is where we bring in our laws of thermodynamics here and do these examples, is we take the change in the internal energy is calculated from the first law of thermodynamics, or delta U is Q minus W. So we get 1400 kilocalories. Notice we want to convert to joules. Remember, joules and calories are both used in heat and energy, but they're defined differently. Remember, a calorie is the amount of heat it takes to raise the temperature of water from, I believe the number, it's about 14.5 degrees Celsius to 15.5 degrees Celsius at atmospheric pressure, whereas a joule is what we've seen from mechanics and other examples in this class as the work or energy done when you act on an object with a 1 Newton force over 1 meter. So we're going to convert that kilocalories to joules and then subtract off the work from that, the work done, and you're going to get, if we do this, we see this is the number of joules. Notice it's actually very large, minus the 6.262 times 10 to the 5. This is actually quite a bit bigger. This is 5.86 times 10 to the 6. So this is going to give us a final value of 5.2 times 10 to the 5 joules. Hope you've seen how useful this can be and how these problems can apply to things you're going to do in your everyday life with thermodynamics.
So, last thing we have here this week is an example of a thermodynamic process. So what we're going to see here is an ideal gas expands at a constant pressure of 3 atmospheres from 400 milliliters to 660. Heat then flows out of the gas at a constant volume, and the pressure and temperature are allowed to drop until the temperature reaches its original value. Calculate A, the total work done by the gas in the process, and B, the total heat flow into the gas. So for part A, Work is only done in the expansion at constant pressure, since there must be a volume change to have work done. Okay, so work equals P delta V. So the pressure is 3 atmospheres times, we have the conversion of pascals to atmospheres, which is 1.01 times 10 to the 5 pascals per atmosphere. Pascals are Newton per meter squared. Then we take the volume difference, 660 times 10 to the minus 3 liters minus 400 times 10 to the minus 3 liters. And then our conversion from cubic meters to liters, which gives us a final answer here of 79 joules. Now this is where we don't even have to do any more calculations, but just look at the process. We use the first law of thermodynamics to find the heat flow. Notice that since the temperature change of the entire process is 0, so there's no change in internal energy, or delta U equals 0, so this gives Q equals W, and thus the heat added is just our same answer for part A, which is 79 joules. Okay, that covers everything for this week, and honestly the class. Again, make sure to check out all the lectures, and let your professor know if you have any questions at any time.
Let's do one last example here. Another thermodynamic process. Consider the following two-step process. Heat is allowed to flow out of an ideal gas at a constant volume, so that its pressure drops from 2.2 atmospheres to 1.4 atmospheres. Then the gas expands at constant pressure from a volume of 6.8 liters to 9.3 liters, where the temperature reaches its original value. See figure 15.22 for an example. So now we want to calculate A, the total work done by the gas in the process, B, the change in internal energy in the process, so the entire process, and C, the heat flow into or out of the gas for the process. So if we examine this, we notice there is no work done in the first set since the volume is constant. Okay, notice there was only a pressure change. So the work done in the second step is given by our good old equation here, P equals delta V. So we want to, first we have to realize where's the pressure at this point, and notice it goes from 2.2 atm to 1.4 atm. So we're going to convert that to pascals like we did before, and remember a pascal equals a Newton per meter squared. Or as a reminder, 1 pascal equals 1 Newton per meter squared. So we're going to put that in. So it's 1.4 times 1.01 times 10 to the 5. Pretty much stays close. It'll end up being about 1.01 times 10 to the 5 newtons per meter squared. The volume difference, it's the final minus initial, so it went from 6.8 to 9.3. Then you're going to multiply by the conversion of how many cubic meters there are per liter. 1 cubic meter is 1,000 liters, so that means there's 1/1000th of a cubic meter in a liter. Multiply all those through, and you get a final answer of 3.5 times 10 to the 2 joules. So we see we can calculate this out as, if I clear this out, 1.4 times 1.01 exponent 5, right, so 1414 times, you can do parentheses, 9.3 minus 6.8, okay, equals, and then you're going to divide by 1,000 here. And again, like it says, 3.5 times the 2, 10 to the 2, or about 354. Okay, since there's no overall change in temperature, because notice it says at the in the explanation, it comes back to its original value. There's no change in internal energy, so the change in internal energy here is 0. Now, lastly, again, we apply the first law of thermodynamics. If delta U equals Q minus W, which is the first law of thermodynamics, and we realize delta U equals 0, then this goes to Q equals delta U plus W equals 0, or Q is 0 plus 3.5 times 10 to the 2 joules, or the same amount of work that is done, since there is no change in internal energy, has to be heat that flows into the gas. So we get a nice step-by-step process. We can go through this and use, really only have to do one calculation and a couple conversions, and then use the first law of thermodynamics to determine the change in internal temperature being 0 gives the change in internal energy 0, and then we can use that to calculate the heat added to the gas, which in this case ends up to be the same as the work done. And of course there'll be other variations on these type of problems, and maybe it's not the internal energy that's 0, but maybe the work done is 0, or maybe the heat added is 0, but you can still manipulate the equation in the same way. Most of the time where in many of these you only have to actually do one calculation, and then you can solve the other one just by manipulating the problem. Okay, well, that is the last example for this week. Again, if at any time you have a question, please email your professor, and be sure to come and look at the lab video that's coming up shortly.